Okay. Hello everyone. The title of my talk is elaTCSF, a temporal contrast sensitivity function for flicker detection and modeling variable with refresh rate flicker. I'm Yancheng Cai, the first author of this work. Let me begin with a brief story. So one day you bought an amazing new display with a variable refresh rate mode for smoother gaming. Time to enjoy it. The bad news is you noticed distracting flickers in VRR mode, especially in darker areas. That looks quite terrible. Variable refresh rate flicker has been widely reported recently. So what causes VRR flicker and how can we model its visibility? Let me introduce our three key motivations. First, existing flicker detection models are insufficient for modeling the visibility of VRR flicker. For example, the critical flicker frequency, CFF, is a century-old standard defines the frequency at which flicker appears invisible. The lower right figure here shows the human CFF values with different luminance and eccentricities. However, CFF focuses on only high contrast flicker for on off, while VRR flicker occurs at much lower contrasts. To model flicker visibility across different contrasts, the temporal contrast sensitivity function TCSF was introduced, describing the relationship between human flicker sensitivity and temporal frequency. Sensitivity is defined as the inverse of the contrast threshold at which flicker becomes just noticeable. Here are flickers at 5 different frequencies. Humans are generally more sensitive to flicker in the 8 to 16 Hz range. And in 2023, TCSF IDMS was established as the industry standard for flicker detection, as shown on the right. However, it doesn't account for other key factors affecting flicker visibility such as area and luminance. While some contrast sensitivity functions do incorporate these parameters, they cannot handle extreme low spatial frequencies or large areas. One thing is note that the CFF is typically equivalent to the frequency at which the TCSF sensitivity equals 1. Although our work originated with VRR flicker, our goal is to develop a flicker detection model applicable to all kinds of flicker. The second motivation stems from a 120-year-old debate: is flicker more noticeable in peripheria? Some studies report that CFF is peak in the peripheria, but others think that the fovea is more sensitive. The third motivation is that traditional flicker detection models considering eccentricity typically only use one eccentricity value as the input. However, many flickers span a very large visual field, making a single value insufficient. To further investigate VRR flicker, we conducted a VRR flicker sensitivity experiment and constructed our datasets. We first present the cause of VRR flicker visibility. Actually, the luminance exhibits subtle differences across different refresh rates, and we utilize this equipment and configurations for experiment. The top left figure here shows the measurement results with time on the x-axis and luminance on the y-axis, including 4 signals with different average luminance levels. Display luminance shows distinct waveforms under different refresh rates with here the vertical lines marking wavelengths. The right figure here shows the Fourier transform results with the temporal frequency on the x-axis and the amplitude on the z-axis. All 4 signals exhibit a low frequency peak corresponding to the frequency of RR switch, with peak amplitude denoted as delta L. So the contrast of VRR flicker is defined as delta L divided by the average luminance, and the VRR flicker frequency is defined as the frequency of this peak. Here we model the relationship between VRR flicker contrast on the y-axis and average luminance on the x-axis. The results show that VRR flicker contrast decreases as average luminance increases, explaining why VRR flicker is more noticeable in darker regions. Here we show the procedure of our psychophysical perception experiment. A total of 16 observers participated, aiming to determine the contrast threshold for perceived VRR flicker. The experiment consists of two stages, MOA and Quest, with examples shown in this figure. The figure here shows our experimental results, with the x-axis is the frequency of refresh rate switch and the y-axis is sensitivity. The data include 4 stimulus sizes, discs with diameter of 0.5 degree, 1 degree, 16 degree, and the 4 screen. 3 key observations can be made. First, humans are more sensitive to flicker around 8 Hz, and also the larger the area, the higher the sensitivity. And also, for smaller stimulus, sensitivity drops rapidly at frequencies above 8 Hz. Here we present the diagram of our elaTCSF model. The process begins with 4 input parameters on the left. Sensitivity functions are constructed for the first 3 parameters, and their product forms the preliminary elaTCSF. Finally, the spatial probability summation model is applied to contrast the complete elaTCSF. Here we address our second motivation, whether the peripheria is more sensitive to flicker than the fovea. First, recall that CFF corresponds to the frequency at which sensitivity equals 1. So as shown in this left figure, the TCSF shape changes with eccentricity, becoming flatter as eccentricity increases. Consequently, as illustrated in the middle figure, the peak sensitivity in the peripheria is lower in the fovea. However, in the right figure, we can find that the CFF in the peripheria is higher. For our third motivation, we utilize the spatial probability summation model to account for very large area stimuli, which operates similarly to a two-dimensional integration. The results are shown in the figure. The table here compares our elaTCSF with other state-of-the-art CSF models. We evaluated 8 flicker detection datasets, including those based on CFF and sensitivity measurements. 2 metrics were used for comparison. Sensitivity RMCE, which measures the RMC loss between predicted and actual sensitivity, and CFF RMCE, which evaluates the RMC loss between predicted and actual CFF. The first row, TCSF IDMS, represents the current industry standard for flicker detection. However, it only considers temporal frequency and neglects other parameters, resulting in poor performance. In contrast, our elaTCSF outperforms all existing CSF models across all metrics. Here it demonstrates an application of elaTCSF, predicting the refresh rates needed to make low persistency flicker invisible in VR displays. The figure uses 3 advanced VR headsets as examples: Apple Vision Pro, Microsoft HoloLens 2, and Meta Quest 3. The x-axis represents the luminance and the y-axis represents the CFF, the threshold frequency for flicker visibility. elaTCSF can predict the CFF luminance relationship with curves. The area above the curve indicates that the flicker is invisible, while the area below shows that potential flicker visibility. Vertical dashed line marks each headset's peak luminance, and horizontal lines represent their official refresh rates. The results show that the higher the luminance requires higher refresh rates to eliminate flicker. For all 3 headsets, their maximum luminance may still result in visible low persistency flicker. In summary, our work includes three main contributions: developing a general flicker detection model elaTCSF, creating a new VRR flicker detection dataset, and demonstrating various practical applications. Special thanks to all my collaborators. For more details and access to an interactive tool for a simplified version of elaTCSF, please visit our project page. Feel free to contact me via WeChat or email with any questions. Thanks for listening.